Hey AP Chemsters, this is Mrs. Vandewall bringing you another edition of the Blank Wall series. We start today with Chapter 14, Chemical Equilibrium. And this is different from Chapter 13, where we just were worried about how fast reactions are going and their concentrations, how much they're being used up, how much time it took. But this is all about equilibrium. We got to continue this story because it's not over with yet. So it says, up until now, we've assumed that the reactions will always go to completion, as in the BCA table. If you remember what BCA stood for, it's before, change, and after. One reactant will be completely used up. However, we're going to find out in this chapter that's not always the case. Now, what I'd like to do is take a look at my little demo over here. So I'm going to turn it like this. And if you look at the bottle, you'll see where it is colorless liquid with some kind of, empty space. We know better than that. There's really gas in there. And so what am I going to do? Well, with the help of Taylor Swift, I would like to shake it up, okay? So I'm shaking up, and oh my goodness, look what happened. It turned to blue. Hey, kind of like my color here. So it's turning to a blue liquid, and so what's happening here? Did I use up all my reactants to make my products? Is this reaction over with? Is it completed? We're going to find out, and we're going to use this to talk a little bit more about chemical reactions. So the concept of dynamic equilibrium is the condition in which the rate. Now let's just stop right there. What the heck is a rate? Well, do you remember from chapter 13, we defined rate as a change in concentration or the change in time. So let's kind of finish off this statement. It's a condition in which the rate of the forward reaction or the change in concentration over change in time of the forward reaction. What's a forward reaction? Write this down. Is when the reactants go to products. Equals, we knew there had to be something equal there because of dynamic equilibrium. The word equal is in the word, so it's equal to the rate, in other words, the change in concentration or the change in time of the reverse reaction. Well, what the heck's the reverse reaction? It's the products making the reactants. Well, wouldn't you know? Look at my bottle. What happened to that blue color? Well, that blue color is almost all gone. Why is that? Because the blue products is now making the colorless reactants. This is a reverse reaction because if I shake it up again, it will go blue, purple, I don't know what you can call it. And if I wait a little bit, guess what? It's going to go colorless because my blue products are going to make the colorless reactants. Oh, that's what that means. Yes. Okay. So let's take a look at this picture here. Okay. We have some clocks. Obviously, time is a factor, kind of like last chapter. What are we dealing with? Well, here's my reaction. We have H2 plus I2 making 2HI. Take a look at the pictures here. The small kind of light colored is the H2, the larger kind of gray is the I2, and then the blue, it looks like it's the HI. So over here, this is at the initial onset of the reaction. Do me a favor, let's write down how much of each reactant we have. If you were to count, go ahead, count. Yeah, you have 8 H2s, and you have, count, 8 I2s, and you have 0 HIs. But notice, after 16 seconds or so, here's what's going on in my little microscope there, okay? I can see that things have changed. If I were to count and write this down, how many H2s do I have in this beaker? Only got 6. How many I2s do I have? Well, 6. How many HIs do I have? I have 4. And if you were to set up a BCA table right now, you're going to see that the stoichiometry works out actually quite well. Okay, so what happens in this beaker? Okay, we're at 32 seconds, so more time has gone on. And it probably won't surprise you where if we were to count up everything again, we have 4 H2s, we have 4 I2s, and we have 8 HI. So far, this is like, well, nothing's new. But look, we would expect after another 16 seconds that pretty much all this would be totally used up. Okay, so we would expect after 48 seconds that you would have pretty much all HI left and no H2 and I2, but that is not the case, is it? You're going to notice that you have the same concentration as at 32 seconds. We still have over here, if you want to write that down, 4 H2s, 4 I2s, and we have 8 HI still. The concentrations did not change. So this is what we call at equilibrium. Well, why haven't they changed? Well, possibly if you look at the coloring of each beaker, they're not the same HI molecules. Well, you could say, well, maybe they moved around in the beaker. Well, maybe they did. Or here's another example. Maybe these two down here collided, forming the reactant molecules, and the reactant molecules collide to form the product molecules. So this is what's called a dynamic equilibrium, that there's still collisions going on. They're still making new products and new reactants, but at the same rate. So the concentrations do not change. So let's look at the graph here and see how this relates. Well, if you look at the graph at 0 time, we have the maximum amount of H2 and I2, and we have 0 HI. As time goes on, notice that we're dropping the amount of H2 and I2. Notice we went from 8 to 6, and notice we're going up quite a bit. We go from 0 to 4. So this graph is actually pretty accurate as depicting what's going on. And then after 32 seconds, notice that we now have 8 molecules of HI and only 4 each of H2 and I2. These are actually supposed to be the same line, but you wouldn't be able to see they're the same line, so that's why they separate them. They are actually supposed to overlap. So then what? After 48 seconds, notice our concentration has not changed. It is still 4 molecules of H2 and I2 and 8 molecules of I2. So the concentrations have not changed. The rate, the change in concentration over time, has not changed. Therefore, it's an equilibrium. Why is it dynamic? Because there's a still idea of the reactants making products, products making reactants. Oh, kind of like over here again, isn't it? So here I have my colorless solution. It was made again by the blue colliding, making the colorless. So here I have exactly what I started with. So I know you want me to. I know you want me to shake it, baby, again. Let's do this. This is so much fun. I can do this all day. Notice it's back to that blue color again. So let's keep our eye on it and see if my products make my reactants again. That's what's called a reversible reaction, by the way. Oh, kind of like over here. So let's keep going. Let me kind of move this over. We have a dynamic equilibrium. What does dynamic mean to you? Think of the word thermodynamics. What does thermodynamic really mean? Moving heat. So like heat being released, heat being absorbed, heat going from high concentration to low concentration. Yes. Or from hot to cold. Dynamic means motion. So reactions continue to take place. Reactant molecules converted to products. Will you please write this down? That's your forward reaction. Okay. Products continue to be converted to reactants. That's your reverse reaction. Forward and reverse reactions take place at the same rate at equilibrium, and general reactions are reversible. This is shown by the double arrows, kind of like this. This is a reversible reaction. Notice that the blue is already starting to fade as the colorless starts coming through. What is a static equilibrium? Well, static means stopped motions. Okay, so static means nothing's going on. So this is what we've always assumed by the BCA table. So no reaction is continuing to take place after a certain time, that all product molecules will remain products. That's why we can say, you know, we have a certain amount of products at a certain amount of time. That all unused reactants, the excess reactant molecules, remain unreacted. And typically this happens when you're going to make a solid or a gas. Solid we call it a precipitate. I don't know if you remember that. So if you're going to make barium sulfate or lead-2 iodide, that would be a static equilibrium because you are not making any more products. But if you have an aqueous solution, or if you just have all gas molecules and you're not creating a gas, then we can talk about dynamic equilibrium. So what, again, I've already mentioned this, the causes of equilibrium. At the beginning of a reaction, only reactant molecules exist. So the only reactant molecules are going to collide collide to make products. But what happens as this reaction continues? You are making more and more product molecules, which then can collide to make the new, or to make the original reactant molecules all over again. So this is what we call the reverse reaction. So again, at equilibrium, the idea of the reactant molecules colliding to make products is at the same rate as the product molecules colliding to make the reactant molecules. So let's take a look at this graph down here, and actually problem number 1 wants you to compare this graph to the one on the front page. So why don't you pause this and see if you can't make your comparisons. All right, so we have here a difference. Hopefully you saw the y-axis is different. The y-axis on page 1 is actually concentration. The y-axis here is reaction rate. Notice something else, that the concentrations really didn't become equal at the end, did they? The HI was higher up than the H and the I2, but look what happens when reaction rate is your y-axis. You start with the forward reaction is very quick to start with. The product molecules is very slow to start with. Why? Because you don't have that many product molecules, so there isn't that many collisions, so you have a very low reaction rate. But eventually what happens? Notice that the rates overlap. Those lines overlap because the rates are equal. So those are the two major things you should have picked up on as the main differences. So let's go to the next page. Okay, this is another example of equilibrium called the Haber process. If you're from Germany, you'd say Haber. If you're a good old American, you'd say Haber. So anyway, the Haber process, Fritz Haber was a fairly young scientist in about 1900, and there was a big question mark in the year 1900. Will there be enough food to feed everyone? The techniques, the improvements, I'm trying to say, in farming had not improved. Farmers are still using a lot of the same techniques they used in years past. There wasn't a lot of huge gains in agriculture, so they weren't making a lot more food. But what happened to population? Oh, it's exploding. Think of the Industrial Revolution and everyone flocking to the cities. Populations are just growing by leaps and bounds. So the big fear was, is there enough food to feed everyone? Well, what are you going to do? Let's make some more fertilizer. So Fritz Haber found a fairly cheap way to make more ammonia, which is used in fertilizer. And therefore, he was, in a sense, saving the world, all right? He found a way to make cheap ammonia. So he took the nitrogen that's already in the air, he added hydrogen gas with that, and he made ammonia. Notice the double arrow. It's a reversible reaction. So let's take a look at this. Notice that at beginning, the H2 is declining really fast. Well, why would it go very fast? Because it's consumed at 3 times the rate of nitrogen, because that's your coefficient. Notice your nitrogen rate is pretty not steep, all right, because it's only a coefficient of 1. And then you are producing your ammonia at twice the rate. So here is at equilibrium. Notice that the concentrations are flatlined. Notice there is no change in concentration, therefore it is at equilibrium. So the rate of the forward reaction, which is making the ammonia, is equal to the rate of the reverse, which is making the hydrogen and the nitrogen gas. Okay, so let me finish up the story. It's kind of an ironic story because Fritz Haber found a way to save the world by making the fertilizer to feed the world, but he also was very instrumental in helping to kill a lot of people. After he came up with the discovery, he got a Nobel Prize, he got a lot of money, got a lot of recognition. Hitler actually brought him into the fold of the German regime, the Third Reich, and he was actually the one instrumental in creating the mustard gas and to gas the Jews in the concentration camps and the political prisoners. So he fed the world, he found a way to feed the world, but then a few years later he killed a lot of people, or his research was responsible for that. So very ironic story. All right, so we're at the end of where we wanted to be. We would like you to go into Schoology to chapter 14, go on this website, click on the video, and fill out this for tomorrow. Have a nice night, and I'm going to end this with another Shake It Up, baby. Here we go. Shake it up. Shake it up. Bye.